In this video, we'll talk about double angle and half angle identities. First, I've listed the identities here for the sum and the difference for cosine, sine, and tangent. Actually, just kidding, I only listed the sum identities because that's what we're going to need to derive the double angle identities. Okay, so I wanted to kind of show you again where these come from rather than just giving you formulas. So let's start with the cosine of the double angle, or 2a. We can think of that as just the cosine of angle A plus another angle A. And then we can use this sum formula, right, where the A and the B are both now just A. So that's going to give us the cosine of A times the cosine of A again, minus the sine of A times the sine of A again. And since these are both the same, it's going to look like the cosine squared of A minus the sine squared of A. This is one form of the identity. I guess we'll do this. There are actually two other forms of this same identity, and they rely on a conversion using the Pythagorean identity. So maybe I'll jot this part off on the side, and then we'll integrate it here. We know that cosine squared plus sine squared is equal to 1 for any angle. If we wanted to solve for either one of these, let's say we wanted to solve for the cosine squared, we could subtract the sine squared of the angle over to the other side. So one thing we can use to derive another identity is this relationship for cosine. We can actually do the same thing for sine squared. So if I wanted to solve for sine squared, I could move cosine squared over to the other side by subtracting. Okay, so let's try that out and see if we can't take what we have and turn it into something else, right? Put a 1 here. How about that? Okay, if we wanted to continue with this, one way to do that is to replace the cosine squared with 1 minus sine squared. So let's do that. We'll do that here. So instead of cosine squared, I'm using 1 minus sine squared, and I still have a minus sine squared of that same angle coming from here. These are the same, so they double up. So I end up with 1 minus 2 times the sine squared of A. This would be the second version of this identity. Okay, the third version, I'm going to start here again. Hopefully this makes sense. And come over here. I can kind of do this same process, but now instead of replacing the cosine, I could also replace the sine. So let's try that instead. So I'm still kind of using this as my jumping off point. Now instead of the sine squared, I'm going to replace that with 1 minus cosine squared. So I'll still have cosine squared of A minus 1 minus cosine squared of A. Think of distributing this negative. Then these two cosine squareds are going to double up. So I have 2 cosine squared of A minus 1. Okay, so the cosine actually has 3 different versions of the double angle formula. Sometimes that's convenient because we don't have to do this in the middle of our, if we're verifying an identity, right, or proving. We don't have to do this in the middle of our work. We already kind of have it done for us by having these 3. And sometimes one of these will fit the situation a little bit better than the other, and that should help us out a lot. Okay, the next one we're going to derive is the double angle formula for sine. So we're going to make use of the sum formula. And just like we did for the cosine, we are going to replace, we're going to use a for both of these. Okay, so we're going to end up with sine of a times cosine of a plus cosine of a times sine of a. Since we can, this is commutative, right? So we can reverse them so that they match. Really, we just have 2 of these. 2 times the sine of a times the cosine of a. So this is the double angle formula for the sine. We can do the same thing for the tangent. So again, I'm going to go back to the sum formula and then put in a for both angles. And that's going to give me the tangent of a plus the tangent of a over 1 minus the tangent of a times the tangent of a. I'm going to go this way. So that's going to be 2 times the tangent of a over 1 minus tangent squared a. Okay, so I hope that gives you a little bit of an idea of where these double angle formulas come from. I don't think these were too difficult to derive, and I think this goes right along with the theme in this chapter of kind of verifying. So I think that's worthwhile. I think next we have an example from the book that does ask us to verify an identity. So it asks us to verify that sine of 4x is equal to 4 times the sine of x times cosine of x minus 8 times the sine of x cubed times the cosine of x. Because we're looking at the sine of 4x, I'm going to take a guess that we're going to need the double angle formula for the sines. Let me bring that in here. Okay, so let's do something similar to what we did earlier. Let's think of this as 2x plus 2x. We could break this up any way that we thought would be convenient. So you could try out different things, but I think 2x and 2x is what's going to work for us here. So just like we've said in the past, we're going to start with one side. I'm starting with this side mostly because I have a formula and I think that might be a little bit easier to use. Like we've said also, right, it's not our only option. If you wanted to start with the more complicated side, which we have recommended as a strategy in the past, that could work for you, and that's fine as well. Okay, so if I'm going to take this as the sine of 2x plus 2x, then I want to use my formula here, right? You know what? I really should have written it like this. 2 times 2x, right? So now I'm going to use this double angle formula, which says that that's equal to 2 times the sine of 2x times the cosine of 2x. Now I can maybe do that one more time. Okay, so let's do that. Now I have just the sine of 2x, which really is going to give me this formula again. So see if I can squeeze all this in here. This will be 2 times the sine of x times the cosine of x. Okay, and now I need an identity for the cosine. Let's see if we can fit this all on the screen. So all of these 3 that we just looked at are equal to the cosine of 2x. Our job is to kind of try to decide which one of these is going to fit our purposes. Remember, we're trying to achieve this right-hand side. And we already have the cosine right here. So I think we really need one that only involves the sine. So I'm going to use this one. I think that might help us out the most. Okay, and it's not written here, but this is equal to the cosine of 2a. So we can just use it as is, where x is our a in this case. All right, so now let's figure this out here. Okay, really have all this, and I need to distribute it to these 2 pieces, right? So all of this is really a 4 sine cosine times 1. So that's going to be 4 times the sine of x times the cosine of x. And then all of this times negative 2 sine squared of x. So that's going to be minus, this is 4 times 2 would be 8. Here's a sine, here's 2 more sines. So sine cubed of x times the cosine of x. And we've done it. All right, so we derived the double angle formulas and we verified an identity using the double angle formulas so that you could kind of see how those play a part. Let's see. Next, we're going to look at the half angle identities. So again, I have those listed here for you. The way we derive the half angle identities is by using some of the double angle identities and then making this replacement at the end. So I'll kind of walk you through that process. Okay, so let's see. We'll start by deriving the sine of a over 2. You can see these are kind of interesting. The plus or minus the square root. So that comes from solving. So if this were sine squared, then to solve for just the sine, that's when the plus or minus square root would come in. So that might tie into some of the things we've already done. Okay, so let's see here. How should we do this? We're going to need to use some of the double angle formulas for cosine. So let me jot at least one of those down right here. So the first one we're going to use is the one with just the sine. Okay, and we're going to take that and we're going to solve for the sine. Okay, and I'm using x on purpose here because we're going to make a substitution at the end. All right, so let's say I really want the sine to be on the left-hand side, so can we do this? Can we add 2 sine of x over here and subtract cosine of 2x over here? Can I do that all in one step? So I'm plus 2 sine squared of x. And then the 1 is staying where it is, and then I'm going to subtract cosine of 2x. Okay, and from here I want to solve for the sine of x. So I'm going to divide both sides by 2. That's where the sine squared of x comes in. I don't want the sine squared, I want sine itself. So I'm going to take the square root of both sides, and I need to use that plus or minus. Okay, and from this point, we're going to allow 2x to be angle A. And if that's A, then this must be half of A, or A over 2. Right, so I'm not changing the relationship at all. This is still double of what this was. I'm just labeling it differently now to match with the format of the half angle identity. Okay. Very similarly, we could do the same thing for the cosine of A over 2. We could take the other identity for cosine of 2x, the one that only involves cosine, and solve, right? And kind of make that same replacement at the end. So why don't I leave that one for you to do on your own if you like. You can fill that in your notes. Let's do the tangent together, because that one's kind of fun. So if I want to do the tangent of A over 2, I know that the tangent is equal to the sine over the cosine. Okay, so when I do the sine over the cosine, I'm just going to put in the formulas that I just had up here or just derived, right? So I'm going to have on the top plus or minus the square root of 1 minus cosine of A over 2 divided by plus or minus the square root of cosine of A plus 1 over 2. So this one came from here, right? And this one came from here. All right, if I'm dividing two square roots, I'm allowed to put them together into one square root. I don't have to worry about these plus or minuses, because if I have two pluses, I'm going to be a plus, or two negatives, I'm going to be a plus. I have one of each, a plus on the top, a negative on the bottom, or a negative on the top and a plus on the bottom, I'm going to have a minus. So I can just kind of combine those two together to be one plus or minus. That's something I can do. I'll have a giant square root. I'll have this fraction on the top. So here's another fraction within a fraction. I'm going to go ahead and flip these around. This is probably a good place to do them. Since they're added, it doesn't matter the order, and the formula shows it in this order. Okay, so then to get the final version, I have to do the keep, change, flip. So keep this one. Why don't we write that off to the side? Keep this one. Change it to multiplying, and flip this one. The 2's are going to cancel, and I'm going to be left with plus or minus the square root of 1 minus cosine of A over 1 plus cosine of A. Alrighty, so that's kind of where those half angle identities come from, and we can use those when we need to for verifying or calculating lots of different places. I chose one example from the book just to kind of give you a use for this. This one's more of a calculating type example. So it asks us to find the sine of the half angle x over 2. Given that the cosine of that angle, x, is negative 5 over 8. And we're told that x is in quadrant 2. So that means the sine of x over 2 will be plus or minus the square root of 1 minus cosine of x is negative 5/8 over 2. There's a little bit of fraction work here, so let's go ahead and do that. So this will be plus or minus the square root. Let's make this 8 over 8. We can do that. These two negatives will make a plus. So this is 13 over 8 divided by 2. Okay, we could do that same keep, change, flip thing here if we need to off to the side. Dividing by 2 is the same as multiplying by a half, right? So this is going to be plus or minus the square root of 13 over 16. Now I can break the square root back up into its two parts since I'm able to take the square root of 16. This will be plus or minus the square root of 13 over 4. Let me add this back in. Okay, but there's one clue we haven't used yet, so I'm going to go all the way back to the top. Remember we said that x is in quadrant 2. Okay, so let's just make sure in quadrant 2 x would be between 90 and 180, right? Not sure if this is what we need to do right now, I forgot, but let's try it anyway. Okay, if we divide everything by 2, then that means that whatever this angle is, it should be between 45 and 90. Okay, so that means that this is definitely in quadrant 1. Do you understand my logic there? So if x is an angle in this quadrant, if I take half of it, then the smallest it could be would be 45. That would be if x were exactly 90. And the largest it could be would be 90 because this would be the largest value for x, so half of that would be 90. So somewhere in between here would be the angle x over 2. Things in quadrant 1 have a sign that is positive. So maybe our final answer would be the positive square root of 13 over 4. All right, well, this concludes our video for double angle and half angle identities. I hope you'll take some time to practice them, and we'll see you in the next video.